So yeah, it's a great honor for me to give a keynote here in the decentralization conference. In fact, I think it was 1997 when I went to the decentralization conference for the first time. And that was actually my first economics conference that I ever participated in. And I met a lot of famous people there, some of which ended up being collaborators like Mark Satterthwaite and Rakesh Vohra and so on, and also Stan Ryder. I think Leo Hurwitz was there, maybe John Ledyard, and so on. So it's a great honor to actually be in this conference as a speaker. So I'm going to talk about sample-based mechanism design. And my hope is that you could actually take some of these ideas and techniques and results and actually apply it to your own research. And let's see. So how we actually got into this is when we started working on what we call automated mechanism design 20 years ago. And that really forced us to think about the practical side of what are really the realistic inputs that the mechanism design box, an algorithm, could actually have. And similarly, what a human working in such a box could actually have in reality. And the motivation of automated mechanism design was to solve mechanism design as a search or optimization problem automatically, rather than the traditional approach where you try to characterize the optimal mechanism by paper and pen. And this creates a mechanism for the specific setting and prior at hand, rather than a class of settings. So it's not like, let's say, the VCG, which is for a whole class of settings. It generates much more like what you might think of as a Meyerson auction in that context, where it's prior dependent. And because of that, it can lead to greater value of the designer's objective than non-mechanisms. And it always minimizes and sometimes completely circumvents the pain implied by economic impossibility results, which are always for a class of settings. It can yield stronger incentive compatibility and participation properties, and can be used in new settings and for unusual objectives. And for some important settings, a concise characterization cannot exist even. So if you're looking for one manually, you might as well stop, because it can't be. For example, we proved that in multi-item revenue maximization, the problem is NP complete. So there is not going to be a short characterization of what the mechanism looks like. And by short, I mean not exponential in the number of items. This also shifts the burden of design from human to AI, which I guess is always a good thing. And often the designer has information about the agents, and it's kind of silly to ignore in many contexts. I'm not saying that, for example, you should redesign the New York Stock Exchange every morning based on the priors you have, but in many cases, the mechanism is run infrequently enough that it's sometimes worth using prior information to redesign it. And I saw this very clearly in our work on sourcing auctions. We fielded over 800 highly combinatorial sourcing auctions. And there, the buyer team often has a lot of information about the supply chain. And it doesn't really make sense to ignore all of that information as a first step of your design process and run some of the standard auction like a reverse auction. And we applied this to many academic applications and two very high stakes sourcing auctions. Now, automated mechanism is not the same as algorithmic mechanism design. They're totally different, although they sound a little bit similar. In automated mechanism design, we are designing the mechanism automatically. In algorithmic mechanism design, the mechanism is designed manually under the constraint that you have to be able to run it in polynomial time, even in the worst case. So let's talk about the complexity of mechanism design. And now, of course, these apply to both manual and automated mechanism design. First, we've shown that many problems in mechanism design are actually NP complete. And this is for the setting where you have as input like a table of all possible preference profiles and a prior on them. And then your output is to say in table form, for any possible vector of revelations from the agents, what is the outcome? And all of these problems that I'm listing here are NP complete to compute the mechanism. So this means that there is no concise characterization. And so if you're actually working on one, this might be a good time to move to something else. But let me put this computational complexity aside for a second. And here in this talk, I'm going to talk about another complexity, which is the complexity of the input itself. So in many multidimensional mechanism design settings, for example, combinatorial auctions, there is also a blow up in the input. So for example, let's say that just looking at a single agent, let's say even in an independent private values combinatorial auction, the support of the distribution over values for even a single agent is doubly exponential. So if K is the number of possible values a buyer might have for a given bundle, you have K to the power of 2 to the power of items, different support points in your prior. And from this, you can see that you are not going to be able to have the traditional prior for any sort of auctions beyond 2 or 3 items. It's too large to store, it's too large to communicate, and it's too large to get the information. So this is the kind of driving motivation of what we call sample-based mechanism design. And again, whether it's manual or automated. So the key ideas to scalability to avoid the complexity of the previous slide and to avoid the need to discretize type space, well, we had 2 ideas. One is to not assume that the distribution over bidders' values is given, but rather to only assume that we have some samples from it. And now this has become an active research field in AI and theoretical computer science, both in the multi-item and in the single item case. And you might say, what are these samples? Let me start by saying what they are not. They are not bids from some strategic mechanism before. So they're not some sort of lies. This is truthful samples from the prior. And where do these come from? Well, originally, the motivation was that they come from a mechanism designer's head. So in sourcing, for example, the sourcing teams could say, well, the valuations could be like this, or maybe they're like that. This is actually a little more likely, and so on. So this information comes from the designer. But of course, if you have been running some sort of a dominant strategy mechanism in the past, and you want to assume that bidders actually bid truthfully, these samples could be from prior bids as well. The second idea is automated mechanism design, or mechanism design, if you like, as such in a parametric mechanism class. So instead of having this type of tabula rasa approach to mechanism design, where you start from an empty table and you try to fill in the table, rather restrict your search of mechanisms to some mechanism family, where every mechanism in the family has some good properties. For example, incentive compatibility or individual rationality or whatever you like. We're going to talk about one example, or many examples with those, and we're going to also talk about one where budget balance is also guaranteed in all of the mechanisms in the class and so on. Okay, so this also can simplify the design a lot. You restrict the class and then you search for the parameters in the class instead of searching for this unrestricted mechanism table. All right, so let me give you an example. Affine maximizer auctions. So you all know the Vickrey-Clark-Groves mechanism. That's what I'm showing here first in this blue box. So we compute the social welfare maximizing allocation. For each bidder, we look at how much worse off they made the other bidders by showing up, and that's how much they pay. And nothing surprising about that. But now in the affine maximizer auction by Roberts, you can actually tweak this so that you boost some of the allocations. And we call these the lambda boosts. And you can also put weights on the bidders. And now the same mechanism applies. It's still incentive compatible and individually rational. But now you got these parameters that you can tweak, the lambdas and the W's, and that can give you better outcomes. For example, a higher revenue. Now, of course, there's a question of How do you tweak those? What's your algorithm? How many examples do you need to know from your prior so that this is actually going to work, and so on. And I'm going to address those questions here. By the way, I cannot see the chat. So if there are any questions in the chat, if the chairperson of the session could read those out, and we can also take some of them afterwards. But if there are any clarification questions, especially, let's take those during. Okay. Then we actually wanted to say, oh, that has a lot of parameters, that AMA, the Affine Maximizer auction. So can we somehow generalize Meyerson's virtual valuations to combinatorial auctions? And you can do a little bit of that, but we show that for incentive compatibility, these functions have to be, the virtual valuations have to be affine. And we came up with this idea called virtual valuations combinatorial auctions, or VVCAs. Here we are having these bidder weights again, but instead of bundling, boosting complete allocations, we are boosting per bidder bundle pair. And if you like, this is a restriction of affine maximizer auctions where the allocation boost has this restricted form where the sum of the over the bidders of these lambda j's of what the bidder gets. And I'm going to talk about these examples and special classes of these. Now, mechanism design as a learning problem. Here, the goal is to, given a large family of mechanisms and a set of Bayer's values sampled from an unknown prior distribution D, find a mechanism with high expected objective value on the unknown distribution D, not just on the samples, but on the unknown distribution D. And that might sound like magic. How could you possibly do that when you haven't seen the distribution? Okay, I'm going to talk about how we do that. The approach here is that we're going to find a mechanism that's optimal or nearly optimal over the set of samples. And then we're going to prove that in a certain sense, you have enough samples so that you are going to generalize to the rest of the distribution, which you haven't seen. And what's a sample here? Well, a sample is a complete valuation draw. So here would be one sample. It would say bidder one's values for all of the bundles, bidder two's values for all of the bundles, and all the way to bidder n's values on all of the bundles. And then the next sample would be a similar draw with different values. And then we have this sample capital N. So this is our input. And you could also imagine maybe in the future to have more selective elicitation of these preferences. We've done a lot of work on preference elicitation, but I'm not going to have time to talk about that today. So here we're going to talk about these complete samples. We have in each sample a value for each bidder for each bundle. And by the way, this approach is not just for auctions. This applies to a lot of mechanism design settings, as I'm going to talk about, but I'm going to focus here as an example on how do we sell stuff so as to try to maximize revenue through pricing mechanisms or lotteries or auctions and so on. Okay, so now this is the most important slide of the talk, and after this you can go to sleep. So, and this might look a little tricky, but I'm gonna go through it fairly slowly and then let's take questions if it's not clear. This is like, if you get this idea, then you might be able to use these techniques in your own work. Okay, so we have this general theorem that applies to any design objective. And I'm gonna try to give you the intuition first. So fix a valuation profile, okay? Now we might get a picture like this. Let's say the mechanism has 3 parameters and we have these hyperplanes dividing the space of parameters for that given valuation, one given valuation profile. And the hyperplanes split the parameter space into regions. And within each region, the mechanism's performance is nice. For example, typically, and in all of the mechanism design settings, we have seen within each region, the performance is linear. So to give you an intuition, think about a single item auction. There, as you increase a reserve price, the revenue goes up and up and up until the buyer no longer buys anything, in which case it plummets to 0. So there, the allocation changed as we went through a hyperplane. So one way to think about it is that within a region in this space, the mechanism has the same allocation and the parameters just change the objective value. But as you cross a hyperplane, that's when the allocation actually changes as well. And then you might get the jump in your objective. All right. So if we have that structure, and I'm going to actually show you something more general first. I'm going to show you a case where these boundary functions don't have to be hyperplanes, and the objective function doesn't have to be linear within a region, because we've applied this to a host of other settings beyond mechanism design. So I'm going to show you the most general theorem that we recently published, and then I'm going to specialize it to this type of a delineable case that I mentioned. So assume the range of the performance function is normalized to be 0 to 1, and that's without loss of generality. Then with probability 1 minus delta over the draw of this many training samples for any mechanism parameters, the expected performance over the unknown true distribution is within epsilon of the performance on the training set. So this says that if you can actually find a mechanism that does optimally or nearly optimally on the training set, it's going to do within epsilon of that also on the real unknown distribution, which you will never have seen so far. And now, what are these numbers in this formula? Let me walk you through that. On the bottom side, we have epsilon squared here, and that just says that the more closely you want to approximate, the more samples you need. So nothing surprising there. And here you have a log of that epsilon squared here. Now, CG star is the VC dimension of the dual class of the boundary function class. So in this case, if the boundary functions are hyperplanes, the dual class of that is also hyperplanes. And then the VC dimension is just a number of dimensions plus 1. And if you don't know what the VC dimension is, don't worry about it. It won't be mentioned in the rest of the talk. And you don't need to know it. So in the case of hyperplanes, just think about that constant being the number of dimensions plus 1. Then what is this T here? T is the max number of boundary functions needed for any one instance. So remember, this picture is for one valuation profile. T is the number of boundary functions that's needed for any one valuation profile to get this nice property that within each region, the function is nice. And what is CF star? That is a pseudo dimension of the dual class of the within region function class. And again, if the objective is linear within each region, as it has been in all of the mechanism design applications we have seen, this is just a number of dimensions plus 1. Okay, so we call that the delineable case if the boundary functions are hyperplanes and the performance objective is linear within each region separated by those hyperplanes. So in this delineable case, we can actually write this in computer science notation and say that it is O number of dimensions, which comes from here, times the log of the number of dimensions times T divided by epsilon squared. So this is how many training instances you need to be able to guarantee that you're generalizing with high probability to the unknown part of the distribution. So now when we apply this theorem, we can apply it to a host of different settings. And it's actually amazing how this applies to many different mechanism design settings.
Tuomas, could we just I think maybe just worth pausing now, because this is your most important slide. Yes. And maybe just give people an opportunity to maybe raise their hands in case they were a bit shy about putting things into the chat.
Yes, I think that's a great idea. By the way, I cannot
is that a good idea?
What is
Indeed. Yeah, so I'm just, there aren't any that have been put in the chat, but I think people are maybe being a bit shy. So I think if somebody wants to just unmute themselves and go ahead and ask the question, now might be a good time. And just to warn you, Tuomas, I couldn't actually see your pointer. I feel like you were pointing at things.
Oh, you cannot see the pointer. Oh, okay.
I couldn't myself, maybe others could, but I couldn't see it. So maybe there are others. So just bear that in mind in case that functionality.
Can you see it now?
Now it's perfect. Yes, I can see it now. Yeah.
Sorry about that. Okay.
Absolutely no problem. I think there were only 2 instances where this happened. If anybody has a question, feel free to unmute yourself and ask at this point. Else we can let Tuomas continue.
Alex, they cannot unmute themselves.
Oh yes, sorry. Oh, I unmute you. My apologies. Sorry, I can unmute you if you just raise your hand and I'll see you. Okay. Oh, Taiwei, did I catch you? Great.
Yeah, thank you. Just quickly, so when you say the distribution is unknown, so when you say probability 1 minus delta is with respect to what distribution, the true unknown distribution, is that correct understanding of the theorem?
Yes.
That was nice and easy. Any more questions?
I like those questions.
we can have more difficult questions. That's perfectly fine. Okay, shall we crack on then?
Okay,
if there's any questions, send it in chat. We're all monitoring it carefully, and hopefully it'll run smoothly. Thank you, Tuomas. Please go on.
Okay, great. So now I'm going to talk about applications of this theorem. And when we do applications, we just have to say how many dimensions there are in the application and what is that number t. So a little bit of reasoning needs to go into that. But with that little bit of reasoning, you get the sample complexity automatically then through this theorem. So let's do mechanism design applications of this theorem. First is posted price mechanisms. Here, the mechanism class is the multi-item, multi-buyer posted price mechanisms. The mechanism designer sets price per item. Buyer 1 arrives, buys the bundle that maximizes his utility. Then buyer 2 arrives, buys the remaining bundle that maximizes his utility, and so on. Now, the theorem is here, the number of dimensions is just the number of items, because that's how many reserve prices we have, or that's how many prices we have, I should say. And the number of hyperplanes is the number of buyers times 2 to the power of items, choose 2. And that's from a simple argument where for every buyer and every pair of bundles, the hyperplane defines where a buyer prefers each bundle. So for each pair of bundles, the hyperplane is really the indifference curve where the buyer is indifferent between the bundles. So once you have those regions fixed, we know for each buyer what is their preference order over bundles, and then the allocation doesn't change, and the revenue is just linear in those prices within each region. Now, moving to another example, 2-part tariff menus. Here we have single item, multi-unit, multi-buyer, 2-part tariffs. You have multiple units of an item for sale. The seller sets an upfront fee and a per unit fee. And if the buyer buys K units, the buyer pays the upfront fee and K times the number of, K times the unit fee. The seller offers actually a menu of these 2-part tariffs. The menu has L rows, so there are L candidates like in the picture. And the buyer chooses a tariff from the menu, so one row from the menu, and the number of units to buy that maximizes her utility. Here, the number of dimensions is 2 to the L, because for each row in the menu, we have 2 numbers, the fixed cost and the variable cost to control. And then the number of hyperplanes is the number of buyers times L times units divided, choose 2. And why is it? It's kind of the same again, why buyers here for each buyer independently. The buyer can choose a row in the menu and how many units to buy. So those are the buyer's choices. And for any pair of choices, that's why we have this choice 2 here. There's a hyperplane that separates where the buyer is indifferent between those two choices, where the choices could vary on the row or the number of units bought or both. A third example, randomized mechanisms or lotteries. Here we're talking about multi-item lotteries for one additive buyer, and this generalizes easily to multiple unit demand or additive buyers. The lottery is represented by a vector of thetas, where one theta per item, and a price P. If the buyer buys the lottery, the buyer pays P and receives each item I with probability theta I. The seller offers a menu of L lotteries for buyers to choose from, and the buyer chooses an expected utility maximizing lottery or buys nothing. Here, the number of dimensions is the number of items times L, and the number of hyperplanes is L squared. Again, from the same kind of reasoning as before of these indifferences, which are hyperplanes. Now let's move to the more complex mechanisms. I talked about the affine maximizer auctions. There we have shown that the sample complexity here is O tilde bidders to the items plus 1 times items. Then when we go to our virtual valuations combinatorial auctions, it's a little less, still exponential in the number of items. And then in mixed bundling auctions with reserve prices, it's just items squared. So now you can see that we have, there's a cutoff between exponentially many samples needed and a polynomial number of samples needed. And then if we go to mixed bundling auctions, it is just a constant number of samples that suffices. We've also applied this to multi-item, multi-unit nonlinear pricing mechanisms and lambda auctions, but in the interest of time, I'm going to skip those. Now, fine-grade auction hierarchies. So we can make these fine-grade hierarchies of more and more complex mechanisms. For example, k-sparse affine maximizer auctions mean that we can just boost k allocations, not all of them. And then we get this containment hierarchy of 1 sparse, 2 sparse, 3 sparse, and so on. The difference between the expected revenue and the empirical revenue on the samples is bounded by O tilde U, where U is the maximum you can make, square root of bidders plus K divided by the number of samples. So increasing K means looser bounds, but a more flexible mechanism, so we can get a higher revenue auction on the samples. So there's an inherent trade-off between revenue and generalization here. Revenue on the samples and generalization. And we have a way to optimize this trade-off. So we pick a mechanism, we pick for it K, the best K, and the mechanism within the family that only boosts up to K as follows. We look at which one has the greatest revenue on the samples minus this red term, which is the same term as you saw before. So which you could think of as a regularizer, and that controls, makes sure that we don't make an overly complex mechanism that looks good on the samples, but it's overfit to the samples and therefore doesn't give you good revenue on the unknown distribution. And again, here's the theorem that this gives you revenue within this bound of the optimal AMA's revenue. And here, if you're really eagle-eyed, you've seen that I'm showing these O tilde results, and you might say, how do you really optimize with O tilde? Well, in the paper, we have actually the full formula with all of the constants. So this gives you a real objective to optimize. Now, we also applied this to voting. So this is not just about revenue maximizing and auctions. For example, here we're optimizing neutral affine maximizers. They're just affine maximizers where you have these mu weights, which we called W's earlier in this talk. We're trying to pick a weight for each bidder such that at least one bidder has 0 weight. And we are doing this redistribution. It's kind of a Clark tax-like taxation. And then the lowest index agent with 0 weight takes all of the leftover money. So that's why it's budget balanced. and the rest of the zero weight agents get nothing. And again, you can apply the same theorem here, and then based on the samples of valuations, find the weights in order to maximize expected unweighted social welfare. So this allows you to kind of balance the social choice with the redistribution aspects, which has been a complex problem in mechanism design. Okay, algorithms. Maybe I should skip this part, but the sort of it is that our generalization guarantees apply to optimal and suboptimal mechanism design algorithms. So you don't have to design the mechanism optimally. That might be too complex. Even if you design it somehow heuristically, the generalization guarantees still apply. Let me skip the algorithm families. Then learning within an instance. Now we're not learning distributionally anymore. We're actually learning from just one instance. And you might think that this is magic. I'll give you an example. So we developed this new general technique for prior-free multi-item, multi-bidder revenue maximization. And it's doing learning within an instance. You draw a participatory set of bidders and from the bidders who actually submitted bids. And then you perform repeated sampling from the remaining bidders to learn a high revenue auction. And then you run the auction on just the participatory bidders. So it's like the classic idea of splitting the bidders into like a market research set and the market set on which to run the market, but you're actually repeatedly sampling the market research set, and that's important. With that, you get strong guarantees that apply without assumptions on valuation functions.
Tuomas, I'm going to give you 5 minutes.
Oh, I don't need that much. We're almost done.
Excellent. You can have it anyway.
Okay, great. Another thing we did is we developed the first theory recently about preserving revenue in a shrinking market. Like think about cord cutters or regular stores when Amazon is taking over and so on. So you have the same bidders who could be your customers, but they don't all show up. And we'll say that each bidder shows up with probability P. How much revenue can the seller guarantee of the original revenue that they used to have? And the setting is an allocational auction, which is more general than a combinatorial auction because bidders' values can depend on what items other bidders get. We show that the loss can be drastic. So it can be more than P to the power of items divided by 2 of the revenue of the VCG even of the original set. For example, with 100 items, and even if each bidder shows with a 90% chance, you can only guarantee 0.52% of the VCG revenue. So not 52%, but less than 1%. But under natural assumptions on valuation functions, one special case of which is cross substitutes, we give the first general revenue preserving guarantee. And that we get with a lambda auction. And there we get something that's proportional to P squared of the actual welfare on the original set, which is much more than the VCG, of course. And then it has these other constants down here. So you can use the same types of ideas for other purposes. And the last thing I wanted to mention is that you can also use these types of ideas for approximating incentive compatibility. So in many mechanism settings, people are actually running non-incentive compatible mechanisms and for various reasons, various good reasons. And the question is, how manipulable are they? So our goal is to estimate how far a manipulable mechanism is from incentive compatibility using samples from the agent's, again, unknown type distribution. And our estimate is a maximum utility that an agent can gain by misreporting on average over the samples if true and reported types are from a finite subset of type space. And our guarantee is that we get a bound on how close the estimate is to the true IC approximation factor. So this allows you to test candidate mechanisms for approximate incentive compatibility in a sound way for the first time. So let me conclude. I presented a general theorem for sample complexity of algorithm configuration, and where the boundary functions can be nonlinear, the functions within each region can be nonlinear, and so on. But in mechanism design, we've always seen that those functions are linear. And this applies to a myriad of mechanism design applications. For example, pricing, many use of two-part tariffs, auctions, both single item and multi-item, lotteries, voting, redistribution, and so on. So this one theorem has a lot of generality in mechanism design. We talked about how do you find the optimal mechanism in a hierarchy of mechanisms. If you the more complex you allow the mechanism to be, the better it looks on the samples, but it's going to overfit. So what is the best balance between complex and simple mechanisms? And now we have a framework for actually formulating that as an optimization problem. And then learning within an instance, instead of learning on a distribution, you can learn just on a single instance that came in. We talked about that, and we talked about estimating approximate incentive compatibility with similar kinds of tools. All right, let's take questions or comments.